Okay, so basically we have 4 regimes for stratified fluid flow, 2-dimensional passing over mountain. Okay, and regime 1 is high flow number. The flow number is large, okay, greater than 1.12, and then you don't have wave breaking, and you don't have braking, upstream braking near surface. And then regime 2. This is regime 2, okay, regime 2 here. Okay, we have hydraulic jump developed, okay, and with braking, okay, and also the braking here and oil braking here, okay, and that's regime 2. And regime 3, this is regime 3, okay, and hydraulic jump is stationary, it doesn't propagate downstream. And regime 4, that's kind of strong braking. So you can see flow coming in will be blocked by the mountain. It cannot, okay, going over the mountain. Okay, and then we talk about the hydraulic jump. Okay, we're talking about the severe downslope wind here. Okay, here, severe downslope wind. And there are 2 major theories. One is resonant amplification theory. Okay, so in this case, the key thing is we have the overturning of the interior flow. So then you overturn it, then you have the so we're overturning. So we are overturning here. So here we have the kind of wave-induced critical level. Okay, and then that can provide a cap of the energy cannot propagate upward. Okay, and a lot of them accumulated, absorbed, and then being kind of advected. Okay, downslope here, and here you kind of build up the potential energy, and then when you get enough energy, then can convert into kinetic energy and rush down here, and then produce hydraulic jump. And so this also, once you have this, also provide a duct, wave duct. So then wave energy is kind of being confined within this lower layer, and so this become very strong, the wind. Okay, and this is called amplification. Okay, resonant amplification. The phase, if the phase going up and coming down in phase, then the resonance happens. Okay, the resonance happens, then the wind becomes very, very strong because wave energy is kind of being ducted in this layer. Okay, and then this layer we have the wave duct. Okay, basically the wave is kind of confined, energy confined here. Okay, so there's nowhere to go, it just rush down the downstream. Okay. Okay, so we have wave-induced critical level, and then from the then you can, I don't know, I think this is probably old version. Okay, I have a new version. This is probably older version, yeah. Because I remember last night I changed this one. Okay. Okay, so that's see here. Okay, the lower layer, you got a lot of wave energy, okay, produced. And how do you calculate? You calculate drag, and that is the wave energy kind of being confined in lower layer. But here, okay, you don't have very high wave energy, and you can calculate the drag, and then also compare with the vertical flux of horizontal energy. Okay. So here unresonant, so here, but with energy propagate a little bit higher, but still a lot confined in lower layer, and that is responsible for, okay, rushing the air downstream, okay, downslope. And in Shinoka and Peltier, they propose 3 distinguished stages for the development of severe downslope winds. This is a very good description, and also you can look at this is older one. Yeah. Okay, I'm not going to go details. Okay, so when you have this this flow, because it's kind of, you have hydraulic, you have lot of mass accumulated here. Okay, when you have four lump is low. Okay, that means slow wind. Okay, and coming in, and then you accumulate it because you cannot go over. Okay, so you accumulate it, and then you elevate the flow. Okay, and elevate the streamline, and then you increase the potential energy here, and then when you got enough, then you rush down and then convert to kinetic energy. So here is supercritical flow, and that's why the wind is very strong here. Okay, and wave energy cannot propagate up because of this cap of wave-induced critical level. If you don't have this, then this kind of disturbance can be forced by mountain, can propagate upward. Okay, it cannot propagate upward. It's because you have the cap there, and this wave-induced critical level kind of provide a cap. Okay, CAP cap. Okay, of the wave energy, and so it goes down, and also this. Okay, this kind of hydraulic flow. When you have the low flow number, and then this goes down here. Okay, so here explain it. A supercritical flow with a severe downslope wind can be found over the lee slope under the wave breaking region. Okay, under here, this wave breaking here. Okay, so you have wave breaking region here. Over the upslope. Okay. And then this one later on will develop into the internal hydraulic jump. This, okay, this eventually is going to develop into like this. Okay, like this. Okay, because wave energy cannot propagate, so then it's rushed down, and wave energy kind of being, okay, kind of accumulated. And then because you have strong wind, so you have strong convergence, and then, okay, flow will be going up, and then also rush down to the downstream. So eventually you got this hydraulic jump. Okay, this hydraulic jump. Okay, and as I said, Shinoka and Peltier's paper has a very good discussion of this theory. Okay. And yeah, here now we have it. So here, look. First, you have a local static instability develops, because as I said yesterday, when you overturns, this means the cold air will be going on top of the warm air. Okay, so then you got upside down. Okay, okay, yeah, upside down. And so here you got cold air here, you got warm air here. Okay, or denser. Probably I should say kind of denser fluid here. Okay, and this is less dense here. Here is less dense. Here. Okay. Remember here, the theta is higher than here. So here you have static instability. Remember here, I said yesterday. So here will go like this, but then this one will be higher than this one. So your theta, I don't know what I use in the symbol. So say theta 1, say theta 2, okay. Then your d theta, dg will approximate equals to theta 1 minus theta 2 divided by delta G. And this way less than 0, that means we have static instability. Okay, so then you got flow, you got instability, then you got things going on, you got that mixing, okay, turbulence comes in. Okay, so then this is the first stage. In second stage, a well-defined large amplitude stationary disturbance is generated over the least slope. So after this overturning instability, then you got this, okay, jump developed, high amplitude wave developed. Okay, that's the second stage. So pay attention to these three. This is a very good discussion. Okay, and that will, okay, give you some guidance before you read the paper. Okay, so you probably can do this first, and then go to their paper, and then come back. Then you get a very good picture. So second thing is once you got this, okay, once you got this overturning because of static instability. And static instability is because the denser air is on top of the less dense air, and then you got upside down. Okay, and then second stage is a well-defined large amplitude wave developed. Okay, over the least slope here. Okay, and here's overturning is normally will be above the mountain peak. Okay, and then here your large amplitude developed. So first, you also get, so this is first stage. Okay, first stage is here. Oh, I think probably you cannot read my writing here. Okay, maybe let me redraw here. So we have mountain, okay, and then because we have high drag flow, okay, normally it's under the low full number. Normally it's under low full number flow. Okay, some people say FR, same as F. Okay, full number flow. So then you come in and then accumulate it, and then you become a low layer. Okay, low layer kind of little bit blocked, and then you got this, and then wash down like this. Okay, so you have high PE. And then convert to kinetic energy. And here you have the wave overturning. So this is the first stage. Okay, you got wave overturning. Okay, and then you got the static instability. And you have the wave induced critical level. Okay, so you have the critical level here, and then you have the static instability. Okay, so that's first stage. And second stage, you got large amplitude wave generated. Second stage. Okay, and this one is going to develop into hydraulic jump. Okay, and then in time, so then here, once you get this stage, okay, then you develop strong shear. Strong shear. Okay, so here there's strong shear. And then you have the Kelvin-Helmholtz instability, or sometimes people just call it shear instability. Okay. And shear instability, that is we call the Helmholtz instability. Okay, Helmholtz. Okay, so this normally people call cage instability. Remember, one time I briefly mentioned about if you have a air flow like this. So say here you got flow go this way, flow go that way. Okay, and then when you have disturbance, what's going to happen? When disturbance is going to steepen like this. Okay, you can steepen like this. Okay. So this when you have disturbance, that's because okay, when the wave goes up, okay, because on top you have flow go this way, so it's going to steepen on this direction, and here, okay, you have wave like I don't know. Today I cannot draw very well. Okay, so you have wave disturbance like this. So what's going to happen here is going to go this way, here going this way. Okay, so it's going to steepen like this. Okay, so this eventually will get instability, and this is called shear instability. And when it happened in the real atmosphere or stratified fluid, okay, it's more complicated than the shallow water. Okay, because shallow water you don't have density difference, but in the real atmosphere or ocean we have the density variation. Normally it's decreasing with height. Okay, so this requires Research number less than quarter. Okay, yeah. So what's the Research number defined? N square UG square less than quarter. Okay. So you require this very small. Very small. So there, if you want to have this to be small, there are two ways to make it small. Can somebody tell me what could be the two ways to make that Research number to be small? You can have either n, okay, n very small, right? You can have that, okay, or u g to be very large. Okay, so probably we can say very small and very large. Okay. Very large. So when it's very small, that means weak stratification. But that can be negative, right? Okay, this can be negative, right? Even better. If this is negative, why? Because negative always guarantee less than 1/4. Okay, so okay, this can happen. Okay, less than 0. So when n squared less than 0, what kind of instability? Static instability. Okay, and you can have this happens. Okay, so here means static instability. It don't necessarily have to be negative, but normally when it's negative, it's very strong. You can induce this kind of K-H instability. Okay, Kelvin-Helmholtz instability, static instability. And when UG is very large, shear is very strong. That gives you shear instability. Okay, so this gives you shear instability. But if you add these two together, add up, that's Kelvin-Helmholtz instability. Okay, so you can have this alone very small, or this alone very large. That's shear instability. This way alone very small, or even become negative, then you have static instability. And this together, because in shear, okay, because this means you need stratification. For shallow water, you don't have this because rho is constant. Okay, and when you together, it's called Kelvin-Helmholtz instability. Okay, and so now what I'm saying there is first on the mountain peak, over the mountain peak here, we develop a wave steepening and overturning, and then become instability, so we have the wave breaking. That's static instability. And that's also kept the wave energy. Wave energy cannot penetrate without them being absorbed or even reflected back, okay, to here. And then once you have large amplitude, and that can develop cage instability because your shear developed. Okay, so both of them happen. Okay, and that's why you had, okay, one is static instability, and then also shear instability. And so we have combined Kelvin-Helmholtz instability. Okay, and that's why we have swung downstroke wind, because energy also cannot, okay. And so that's the second stage. You have the Kelvin-Helmholtz instability, shear instability developed, okay. And normally when we say shear instability, we refer to homogeneous fluid. That means density is constant, okay. And when it applied to the, when shear instability occurred in the stratified fluid, like ocean, like atmosphere, then we call cage instability. Okay, so then the region of enhanced wind here, the region with enhanced wind, okay, on the D slope expand downstream, okay, because wave energy cannot go, and then this potential energy kind of keep converted into kinetic energy, rush down, and so it's kind of expanded downstream, and then develop the last stage, hydraulic jump. They don't say it because they are the group against the group, okay, promoting or supporting the hydraulic jump. That's actually a hydraulic jump. Okay, you can see it from the picture. See here? So here you got wave overturning. See, beautiful theory. You see wave overturning. See here? See here? So here critical level here, right? Wave induced critical level. Okay, we induce critical level like this. And then you got wave breaking because okay, upside down. Okay, you try it. You okay, yeah. You probably can stand for some time, but then somebody kind of, okay, pet you, and then you a bit overturns. Okay, so this is wave breaking because you have which kind of instability? Static instability. Okay, try to take a note. Okay, somebody could ask you the question. Okay, and then this area will expand downstream. You got high amplitude wave. Okay, you got high amplitude wave, and then okay propagate downstream, and then develop hydraulic jump. Okay, so very simple. You see this picture. If someone asks you, okay, briefly describe this. This one is you have wave induced critical level, and then you got static instability, and then static instability make the wave breaking. Okay, that's outside. Okay, wave breaking, and then you got large amplitude wave expand downstream, and here develop into hydraulic jump. Okay, they don't say it in their paper because they are against the idea, but it is hydraulic jump. Okay, from my point of view, I say it clearly in my book. Okay, so that's what they say. But it's a beautiful theory, except the last part, they don't make a link to hydraulic jump. This part actually is hydraulic jump. Okay. Okay, and so that's the theory. And then there are some other theories being proposed, but along this side, okay, like Lin and Wang. Wang is my former student, and then they also kind of along this line, they kind of okay, anyway, so this is, you have the overturning. This is number very small, less than quarter. This one less than quarter. So you got this large amplitude wave develop into hydraulic jump. Okay, so this is in Wang and Lin. We kind of okay, Guan published that. Okay, yeah. Okay, so I guess this means nonlinearity is very important because in Lin and Wang's paper we use okay, the model I developed And that one, we can separate the perturbation and the basic wind. So then we can turn off the nonlinearity. So we turn off nonlinearity. Okay, with nonlinearity, you can have this hydrogen jump developed, see here. But with the turning over, okay, you turn it off, there's no, this linear flow, there's no hydrogen jump developed. So, okay, so this initial disturbance, wave-induced critical level is very important. It can happen because of the nonlinearity. Okay, so it can stiffen and then overturns. Okay, so I probably will kind of let you read it. Okay, shouldn't be difficult to read. There's no equations. Okay, and then hydrogen theory. Okay, that's dated by Smith, 1985. In this time, he's the first one to it, but he's the one theorized it. Theorized means he's the one has the concept put into equations. Okay, so become a theory. Okay, and like remember I showed you the conceptual model like this. I showed you the conceptual model here. Okay. Remember this one? This one. So in older time, people already have the idea. Okay, this zero tons of wind is related to hydrogen jump. Okay, but they didn't put it into theory, into mathematics form. Okay. And Smith is the first one proposed it in 1985 in JAS, Journal of the Atmospheric Science. Okay, so then he proposed that. I probably don't have time to go through his theory. Okay. Yeah, when I was his student, he has a very good 1979 review paper. I go through all the equations, okay, to kind of train myself, and also more or less required by him. Okay, so what I try to say is Smith tries to say, and also the other group, same group of people to say is the hydraulic, okay, state. That means you have strong pressure, gradient force pushing on the mountain, and then accumulated, and then airflow goes up, and then drops down, and this is called hydraulic. Okay, because remember drag is like we have negative infinity to positive infinity, and then we have P pressure, and then dH, okay, and that's equals to negative, and then P prime, dH, dx. Remember that? Okay, that's your strong pressure. And why you have strong pressure? Because your flow is slow. Okay, so you have low flow number flow, you have subcritical flow. So you don't have enough energy to cramp it over. So then accumulate, become deeper. Okay, and then you get enough kinetic potential energy, and then convert, okay, over to downslope wind, which is strong, okay, large kinetic energy. Okay, so potential energy converted in kinetic energy, and then rush down. And they say once you have that two-way interaction between a smoothly stratified flow and the deep wear mixed turbulence state region above the lee slope, okay, and so you need a dividing streamline. That's what he meant. So he kind of simplified the concept, the observed features of the flow. So you have this this is like a shallow water wave, shallow water flow like this, accumulates high enough and then rush down, and then here you have a dead region, because here you got the turbulence and your flow just more or less stagnant there. And then here you got the flow coming in, this streamline coming in, split into this one rush down, and this one undisturbed. So you have dead region here, and this is called splitting. okay, streamline or dividing streamline. Okay. So he did that to develop it. And then since it is nonlinear, so because nonlinearity is very important, so what he did was he based on, now we can apply the section 1. Okay, so he applied this Long's theory. Okay, Long's theory here. And then, okay, and then he gives low boundary conditions. Okay, this mountain, right? Low boundary conditions. Okay, and then you have no disturbance above the upper dividing streamline. So conceptually, you can visualize this. This dividing streamline, one go down and one go undisturbed, just idealized. And then, so you assume there's no flow here. So then you have a upper boundary condition, cap energy. Okay, so that's why I tell you it's kind of, so that cap of the energy is same idea or it is equivalent to this critical level, wave-induced critical level, the cap, the wave energy. And so they don't say it, but actually that is critical level, in wave-induced critical level. Okay, and so in Smith's theory, he assumed, so there are no disturbance here, so then you have a kind of rigid lid. Rigid lid means your wave energy cannot penetrate up. Okay, so only way is to go down, and that will develop this hydraulic jump here, okay, and this is a lot of turbulence here, okay. So then that's his theory, okay, so basically it's like Long's theory, okay, except he assumed you have this, okay, cap here, okay, so that provides the upper boundary condition, and then also he has this, okay, dead region, and that will define, okay, your flow below that. Okay, and then he also based on, okay, the steady state, the Bernoulli equation, okay, around that G equals to H naught plus delta C. And delta C is, okay, the displacement below that undisturbed, okay, dividing streamline go down. This is delta C. This is delta C here. See here? Okay, measure from here. This is divided streamline, upper one, lower one, and then you got this delta C and defined. So you get some conditions, and then he can produce a theory very beautifully of hydraulic jump. Okay, so I'm not going into details here. And then, okay, then he was able to calculate the drag, and he compared with observations, okay, and found very similar, okay. So that's basically, okay, his theory is like that, okay. And then this is in kind of Duran. Duran is a professor at University of Washington, okay. And here, see here, so now, if somebody show you this picture and ask you what are the major features here, can somebody tell me what's a major feature in this, in here? Here's the layer atmosphere. That means the certification are different, okay. Certification are different. So this one, you can see the first tilt, right? That's upward propagating wave. Here, what's here? What's this? D waves, okay. And what's this? Non-hydrostatic disturbance. Go this way. What's this? Hydraulic jump. This slope, okay. This is downslope wind, severe downslope wind. Hydraulic jump, okay. So you can different kind of structure, different layer depth, okay. Then you can produce that, okay. So I think he is using this one to support, okay, kind of compare with Ron Smith theory and then support the hydraulic theory. So the hydraulic theory of severe downstream winds was confirmed by numerical experiments of stratified fluid flow, like by Duran and Cramp. And Cramp, he is the original leader of the developer of the Wolf model. And then Beckmeister and Pierre Humbert, 1988. Okay, and also by laboratory tank experiment by Rotman and Smith. Okay, so here that's a requirement for the this is called hydraulic theory. Okay, based on the hydraulic jump idea, it is necessary to specify the initial height of the dividing streamline. You have to specify it. Okay, thus the dividing streamline height cannot be determined a priori. You cannot determine beforehand. Okay, if the critical level is induced by wave breaking. Okay, because wave breaking, you don't know where it's going to happen because it depends on your flow structure. It's going to happen, but here you have to specify it. Okay, so it's a kind of little bit artificial. Okay, although the theory is very beautiful because it kind of capture, okay, a lot of observed phenomena, but put it into a simple way, and it can reproduce the hydraulic jump. Okay, so this is my own interpretation, discussion about the applications of these two different theories for hydraulic jump. Okay, so basically they have some differences. One of the big differences is the different critical level height for hydraulic, that's a severe wind state, predicted by these two theories. Okay, so then in Lin and Wang and Lin actually, that is part of his thesis. Okay, later in 1999. Okay, and so we kind of we found actually the critical level height is more consistent with resonant amplification theory. Okay, and on the other hand, hydraulic theory predicts critical level heights, okay, like this. Okay, so this discrepancy appears to be caused by different stage. So, in other words, when you start to have this, in the beginning, you start to have this overturning. Okay, that is earlier stage. So you have wave overturns. Okay, and that is created by the wave-induced critical level. And when you have hydraulic jump well developed, this will go down. Okay, so the height will be different. And when in Ron-Smith hydraulic theory, okay, he predicted this height that is afterwards. Okay, when the flow is well developed. And in the resonant Clark and Peltier's theory, that is talking about earlier stage. Okay, so one is occurring in earlier stage. Another one is at later stage when flow is well developed. So actually there's no conflict. Okay. So in earlier stages of a hydraulic state, the resonant amplification theory is consistent with weakly nonlinear theories. Okay, and then it appears the resonant amplification theory focuses on the earlier stage of the severe downstream wind development, while the hydraulic theory focuses on the later stage. Okay, yeah. Take a note. Okay. Okay, so that's it for chapter 8. Okay, so let's take a few minutes break and then come back for starting chapter 9. Okay, yeah, thanks. Okay, we speak English. Yeah. Okay, so next topic is the three-dimensional flow over isolated mountains. Okay, so see, in the beginning, we have the shallow water, homogeneous fluid. Okay, no stratification. And then after that, we have stratification. And then we add nonlinearity. And then, okay, now we are adding the, okay, kind of three-dimensional flow. So we'll study three-dimensional flow over isolation mountains. Okay, in last chapters, we study two-dimensional flow. We also, in that way, we also assume the mountain is two-dimensional. That means it's a mountain ridge, okay, extend to infinity. But in reality, you cannot see that kind of mountain, okay. And of course, sometimes it's close to it. If the mountain is longer, then you have two-dimensional flow can well describe the real mountain if the mountain is a long ridge, okay. Okay, so in reality, we have to add three-dimensional, the three-dimensional flow, and that become more complicated. So linear theory, so now you see here, this is same as before, right? Steady state, implicit, that means no friction, no rotation, and so this is, steady state, no partial U prime, partial T, and this is Boussinesq, here, rho naught is constant, and now we just add one more equation, now we allow partial Y, so three-dimensional, before we assume partial Y equals to 0. No, we have certification. We do. We do. Okay. Yeah. Now here we do. Yeah. Here too. Yeah. Okay. Yeah, we do. We have it is A square certification. Okay. Yeah. Where's certification? Okay. And here. So we have certification. Okay. We are just three-dimensional. We just add up the three-dimensional. So we have this partial Y. Okay. And before for 2D, we assume partial Y is equal to 0 for all the variables. Okay, now this is same as before, right? Same as before. And now we add one more term, partial Y. Okay, so the difference is add this three-dimensional dy. Okay, so now for 3D, dy not equal 0. Okay, so you have to include those terms. And here, same as before. So only complication is we add these two terms of partial Y, partial Y. Of course, this is linear flow. Okay, this is linear flow. So we have assumptions. So if somebody write this set of equation for you, and then you could be asked, is this system is closed mathematically or not? Okay, then you have to calculate. You have to not calculate. You have to kind of count how many variables and how many equations. So tell me, is closed or not? Okay, how many variables? U prime, V prime, W prime, P prime, theta prime, and what? No naught is not. No naught is constant. Okay. No naught is constant. This is constant. Okay. It's Boussinesq. Okay. Okay. And that the no prime come into here. No prime come into here. Okay. Come into here. Okay. Yeah. And so that's about it, right? Yeah. So we have 1, 2, 3, 4, 5. Yeah, so it's closed. Okay. And then and we don't have nonlinearity. Okay, so these set of equations can also be combined into one equation. Okay, and then that becomes like this. It's not that complicated. Okay, just like this before, and we use eta instead of w. But the same thing. You have w, you can, okay, you can have the w sub xx, and this replaced by w. Okay, same thing. Okay, so basically 5.4.6 is equivalent to d square w prime xx plus n square over u square, and then we have there h w prime equals to 0. Okay, and this means we have partial x, okay, plus partial y square, partial g square, and then we have partial w prime, partial x square, like this, plus n square over u square, partial square. This h means horizontal only, so we are only horizontal, Laplacian, equals to 0, like this. Like this. Okay. So if two-dimensional, what happened? This is 3D. So this is 3D. So if it's 2D, what's happened? This term is gone, right? And this term is gone. So then that will reduce to the following. Okay, so that will reduce to partial x square plus partial g square w prime dx square plus n square over u square partial square w prime partial x square. Okay, so you integrate twice, negative to x twice, assuming for infinity. Okay, it's not disturbance for isolated mountain. Okay, then you do twice. That will reduce to what? Where is my red marker? Oh, here. Okay, so this one is gone. This one is gone. So this is familiar, right? Right. This become partial square w prime partial x square plus partial square w prime partial g square plus n square over u w prime equals 0. And this one, we call it this square here, we call it L square. What's L? Score parameter. Okay, so it's correct. Okay, so then you can also use eta, okay, because w prime is equals to u partial eta partial x. Okay, so you can use eta, and then this part is basically follows Wrong-Smith theory. Okay, three-dimensional flow over mountains. Okay, like this. So now you can transform into free space. So now if say we just follow Wrong-Smith symbol, okay, approach, we use eta instead of w prime. Then we have n square over u square, and then d square h eta equals to 0. Then the Fourier transform. Okay. Then partial x corresponding to ik, partial g. So we just do this in x and y. Okay. So partial g is still partial g. Okay. We keep it because we don't do Fourier transform in g direction. Okay. And then partial y will be corresponding to what? I L. Okay. I L. Okay. This L is different from this L. Okay. So this I L. This is the y wave number. This x wave number. The k. Okay. Wave number. Okay. So that's pretty easy, right? Because ddx will be what? This will be partial square, partial x square, partial square, partial y square, plus partial square, partial g square, and then partial square eta, partial x square, plus n square, u square, and then partial square, partial x square, plus partial square, partial y square only. Okay, no g, because this is horizontal, and then eta equals 0. Okay, so then this becomes pretty easy if you use the trick. Okay, so this partial x will become what? Ik squared. So it's negative k squared, negative l squared, plus ddg, g. Okay, and then this become negative k squared. Okay, and then eta. And then this become negative k squared, negative l squared. So it's negative n squared over u squared, and then k squared plus l squared, and then eta will hit. So this is in free space. Okay, then you can get organized. Okay, so this negative cancel out. This negative cancel out. Okay, this negative cancel out. Okay, so then we have this cancel out. So we have, well, probably I just write up. Okay, k plus l squared, and then times eta head. Right, the first two, and then minus k squared, l squared, g, eta head. Okay, and then we have this minus, okay, n squared over u squared. Okay, and then k squared plus l squared, and then eta head equals 0. Okay, so then we have negative k squared, partial square, eta head, partial g squared. Okay, and then these two can be combined. So then we have plus 1 minus n squared over u squared, k squared plus l squared times eta head equals 0. Eta, okay. So this becomes the square eta head dg squared, and then plus n squared over u squared minus 1. Okay, and then this k squared plus l squared divided by k squared, and eta head equals 0. Okay, so that's okay. And you can write k squared plus l squared. You can define this as kappa squared. Okay, so then this will become kappa squared. So this will become kappa squared divided by k squared. Okay, this k is horizontal wave, x wave number. This is three-dimensional wave number. Okay. Okay. Oh, sorry. This is kind of horizontal wave number, and this is just in x direction wave number. And then you can you can solve the problem. Okay, or you can just write just like there. Okay, you can write it that way to m squared. So this part we can write as m squared. Okay, and then you can write that way. That k, capital K is horizontal wave number. Yes? Oh, something wrong?
Yes. The second line, the first term
Second one?
Red.
Red. Oh.
The second one, the first term.
This one?
Yes.
This one?
K square over K square plus L square.
Oh, okay. So this is correct, right?
This term is wrong.
This is
term, yeah.
this second row is wrong. Which one is wrong?
First term.
Come here. Yeah. Come here. I think I'm too close here, so I cannot see clearly. Yeah. Okay. Yeah. Write down what you mean. Yeah. Let me see. Okay. So, no, so here may be right. Let's double check. Okay. So, this term, there's a K here. Right? K here. That's good. Okay. Yeah. So, we have K here. Okay. Right? K. And then we have K here. Yeah, that's correct. And then we have, okay, can I see that? Okay. So, we have, we have K squared. Okay, so this one. Okay, so let's redo it. Okay, let's redo it. Okay, so this means, okay, we have K squared partial G squared, and then eta hat. Okay, so this is done. And then these two, we can have, I see, yeah, that's right. Okay, so we have K squared minus N squared over U squared times K squared plus L squared. That's eta hat equals 0, right? Okay, that is correct now. So this one we define as kappa squared, okay? That's horizontal wave number, okay? And K is X wave number, this is Y wave number. Okay, so then we have the eta hat G squared. Okay, and then we just swap these two, right? Okay, swap these two, and then it will become plus, and then N squared over U squared minus K squared, and then divide by K. So then we have kappa squared divided by K squared, and then eta hat equals 0. Okay, then this should be correct. Okay. And then this one, okay, we can, okay, so we can do this eta dg squared plus, okay, this K, we can divide this K into there. So then we have N squared divided by K squared, U squared minus 1, and then kappa squared, and eta equals to 0. Okay, yeah, and then this is, we define this as M squared, okay? Yeah, so that will be consistent with that theory there. Okay, so then once you have this, that's a piece of cake, right? We keep seeing that, okay? This piece of cake, okay? We keep seeing that, so we know the answer, right? Because we know the solution. We don't even have to look at down there, okay? Because we can solve it. This eta hat will be equals to what? Will be equals to A, okay, e to the I and G plus B e to the minus I and G, okay? And so M squared is defined as over there. Okay, maybe I better to write down here so people can see more clearly. How many people are there? Huh? 5. Okay, so yeah, so we kind of fluctuated from 5, 8, 7, 6. Okay, okay. So we have eta gg squared plus M squared, eta equals to hat. Okay, So we have eta hat is equals to a e to the I mg plus b e to the minus I mg. Okay, and m square is defined as here. Okay, so will be n square over k square over u square minus 1 times kappa square. Okay. So if n square and k square over u square is greater than 1, then that means m is real or imaginary number. If n, this will be greater than 0, right? So this whole thing will be greater than 0. So when you take the square root, it's going to be, okay, real number. It can be positive or negative, but it will be real. Okay, if n square divided by k square times u square is less than 1, then this will become negative. Okay, so we take square root of this right hand side will become imaginary. And that will be like we did it before. Okay, we have two types of flow. If this is real, then this will oscillate in vertical. That means wave energy can propagate up. That's vertically propagating wave. If it is less than 1, then m is imaginary. Okay, and then imaginary, that means this will become negative n. Okay, and then we have positive n here. Okay, if we can write m equals to I times n, we've done that before, and then this become e to the lambda g or a plus b e to the minus lambda g. Then you have different regime because that is you have the evanescent flow. You have to have bounded solution on top of the upper boundary. So then you can solve this. Okay, and we have done that before. So then the solution, okay, we can solve it. And then you take the double Fourier transform back. You take double Fourier transform back. Okay, and this one is not one-sided. Okay, this is complete regular Fourier transform. You make transform back. This is Fourier transform forward. This backward. Okay, and then you can get the solution. Okay, and the solution depending on, just like I said, it's n square over k square u square is greater than 1 or less than 1. Okay, and this one will be upward propagating wave. This one will be evanescent flow. So no surprise now. So now the good thing is we learned some basics. So now we don't have to explain everything because we have the experience of doing this kind of problem, except it's just more complicated. Okay, yeah. So if it's two-dimensional, this become k square. Okay, k square, and that will be reduced to what we had before. Yeah. Okay. Yes. My taxi is coming, so we have to go. Good news, right? Yeah. Okay. So then you apply low boundary condition at g equals 0 equal this. Okay, and then you make Fourier transform of the low boundary condition, and then you try this, and then you solve the problem because you apply upper boundary condition. Okay, if this is real, then you pick up this one, delete this one. If it's imaginary, this become negative. This become negative. This positive, and positive one is amplified with height. So we delete this one. So we can have solutions. Okay, so now you can, and then this is three-dimensional Fourier transform of the lower boundary. Okay, and then you can non-dimensionalize it, and then this is what worked up by. Okay, so I had to finish in a couple of minutes, and then I go downstairs, and then I go down there. Okay, yeah. Good. So then transform back will be very difficult. So then Ron Smith used the first Fourier transform to transform back to the physical space, and you can still have solution. So it's kind of theory, but it's kind of combined, kind of analytical approach and the numerical approach. Still kind of idealized, still kind of theoretical study. So in some of my series, I published paper before. I also sometimes combine together. Okay, sometimes I have the whole analytical solution. Okay, but sometimes I also apply the fast Fourier transform, and then you can get a solution here like this. Okay, get like this. Okay, so then you feel like okay, your disturbance like this kind of U-shaped disturbance. Okay, but at different height, you have different patterns. Okay, the same pattern, but your upward motion is here. But for higher level, then your upward motion is shaped here instead of over the mountain. So it kind of vertically there are different wave patterns. Okay, so I think I probably have to continue next week. Okay, of this. I probably will not go into great detail of the mathematics, okay, although I don't think you cannot understand them, okay. So I encourage you to read these during the weekend, okay, during the weekend, and then, okay, we'll go over Tuesday. Okay, yeah, thanks. Okay, yeah, so have a good weekend. See you Tuesday.